Okay, guys. Now that we heard like our introductory talk to blockchains, we are going to the second talk of the day, which will be blockchain scalability, a holistic recap from Kian, who is a Polkadot core developer. And yeah, since I've started with blockchain, scalability has always been like a topic. And so I'm really excited to hear and learn more about blockchain scalability. Kian, the stage is yours.
All right, thank you for having me. Yeah, I think this talk fits very nice with the previous one based on what I heard so far. So let's get started. A little bit of intro first about myself and my intention with this talk. So my name is Kian. I've been part of the Polkadot ecosystem for about 6 years now, contributing to the development of the protocol in various ways. You can find my handles to follow or my blog post here if you wish to know further about this talk or my further publications and so on. My purpose in being here is that over the last year or so, I have increasingly sensed that as an ecosystem, not Polkadot per se, but blockchain ecosystem as a whole, we are perhaps lost sight of the original purposes and goals for which we started to build. It's a sense of dysphoria, the opposite of euphoria. I hear, new tech being built here and there, and I sometimes I have lost the connection of like what was the relation to what started this ecosystem 10 years ago, or the things that I knew 6 years ago when I started. So I'm personally on a journey to try and rediscover these things, which means unlearning a lot of things that I knew about blockchains from secondhand, words that other people have told me, relearn them from scratch, and I'm rebuilding my foundations here. And part of this journey has led me to rediscover how blockchain scalability works and build a mental model around it. And today's talk is this slice of my broader philosophical pursuit. Finally, despite being affiliated with Polkadot and spending more than half a decade of my life on it, I'm really not here to sell a product or protocol to you. I'm here to teach and try to propagate the understandings that doesn't particularly perhaps help you choose the platform for your next, meme coin launch or something, but really discover what is it that we can do with these blockchain technologies. So I'm looking at broader questions here. All right, to set a little bit of orientation, we need to go back to this age-old example of owning digital money. This helps us have a common foundation before we can get to the actual scalability part. So let's look at the very well-known example of owning, let's say, 1,000 euro in a bank like Revolut, or maybe a German version of it, Sparkasse or DKB or something, and owning 1,000 euros in Bitcoin network. How is it that I believe both of these 1,000 euros exist? How is it that I trust each of them to exist? In the traditional banking one, there's a form of trust that eventually I coined conditional trust, in that it's conditional on the existence of governments, regulators, banks following rules, and at the very foundation of it, law enforcement, military, police. And therefore, when I make a transfer on this like Revolut model, I trust that it will happen. And if by any chance it doesn't happen, there's a justice system I can go to. If a judge votes in my favor, I know this thing will happen. So these are all like these man-made forms of trust that I eventually named conditional trust. And how is the equivalent in the Bitcoin network? Like, is there like this judiciary system in Bitcoin? Is there a Bitcoin jury that I'm not aware of? No, none of this really exists. In the Bitcoin network, or equivalent in Ethereum, in Polkadot, in Solana, in all of them, we synthesize a different type of trust that I would call it verifiable trust. Instead of being based on these conditional man-made institutions, this new type of trust is based on branches of science, such as mathematics, such as computer science, such as game theory, such as economics. Or more often these days with the advent of ZK cryptography. To give you an example, like one of the foundations of Bitcoin is, for example, that a hash function is irreversible and works as it does. And a hash function is irreversible no matter which country in which it's being executed or in the hands of whom it is. These are like properties of these networks that we are stitching together and out of which we are building this new form of trust. So it's very important to remember the difference here. This is a new synthesized artificial form of trust, but crucially it's verifiable. And I think it's very important that as we are embarking on the journey of scaling these systems, which I will get to next, we keep our gaze back at this property, how much we are sacrificing this verifiability. Finally, a small detail of this verifiable trust, which I think the previous talk would help you understand it now much better, hopefully, is that very often these branches of science come together and have some entities that broadly we call validators, play some games that involve redundancies. So in short, many blockchain networks, especially the proof of stake ones, contain this group of entities called validators. They are often backed by some economic security, which means they have some capital at risk, which is basically the guarantee of why we believe they do their computation correctly. And they have to do a lot of redundant work. And in the simplest model, these validators usually form a committee. They take turn. One of these validators who is currently the leader proposes a change, everyone else verifies, then they move to the next step and so on. So it involves a lot of redundant work, and this redundant work, is there a chance we can get the text in the slide? I mean, not a big deal, but so with this understanding, we can build this two computational model. You can't see the text on the big screen, but I can tell you what it is. It reads, a secure validator set working together is like one massive, slow, and trustworthy computer. So if we look at the Revolut model, the traditional model, if we want to transact with this system, there's no constraint. Like as little as one computer somewhere in the world can hold this information that I own 1,000 euro or whatever. And if I want to transact, I just have to authorize myself to this computer and that's it. So there's really not this constraint of scalability in the sense that we have it on the Bitcoin model. Whereas in the Bitcoin model, we can see that these blocks of work, they have to go in sequence. I cannot have all Bitcoin miners do some work for me all at the same time. Things have to happen in coordination. And this group of validators working together is the core reason blockchains have a hard time scale. Or in some ways, I can say it's the core reason why they are secure. It's also the core reason why they are slow. But anyways, the main takeaway I want you to have from this slide is that we can model the entire validator set of a network like one big computer, one big, slow, trustworthy, single-threaded computer that can only process information in a very slow, sequential manner. And then the question at hand, well, there's two questions at hand, if you want to be a little bit philosophical, is that, which of these two computation models we want, or in which instances perhaps the verifiable trust that the Bitcoin computer provides is better than the conditional trust that traditional computers provide. But that's not the purpose of this talk. The purpose of this talk is to say, if all of these validators are one big computer, how can we make it go faster? Okay, just to know that my text is still not there, but that should be fine. I think you should see all the diagrams. Okay, so scaling options. Let's look at the first one. The first scaling options is to not tackle this problem really at a architectural level and say, this blockchain, I just keep it as it is. And the work still happens sequentially. Let's just have these validators be very fast, I call them sci-fi validators, have them have enormous amounts of CPU, RAM, disk, and also deploy a lot of software tricks like parallelization to try and make the system go as fast as you can. This system is analogous to what we know in traditional systems like vertical scaling, and we kind of know it can only get us so far. It gets us to a certain extent, in my opinion, pretty good, But there's a reason that normal cloud or normal distributed system at some point also decided to go in the direction of horizontal scaling versus vertical. That being said, a very good benefit or positive thing about this model is that it introduces no fragmentation. As we get to the further scaling options that are mainly L2s and rollups and so on, we will soon see that they all introduce one way or another a form of fragmentation. And this system doesn't have that because it's one fast machine. It's like no multi-chain things going on there. And finally, another downside of it that I would just pose more as a question is that I think it's very important, again, to keep in mind that at which point these optimizations or these hardware constraints that we impose on for example, full nodes or validators are equivalent to basically cutting corners in that original verifiable computer model. Broadly speaking, Solana is a network that adopts this approach in terms of scalability. It's less about multi-chain, and it's more about having one very fast chain. All right, this is where we get more into the multi-chain aspect. So then we can look at if you remember the original model, we might have, for example, 1,000 validators securing one network. And we might say, well, let's split this 1,000 validators into 10 buckets and then secure 10 networks with them. How about that? I'm doing the same thing in this diagram, except it's just 3 smaller groups of validators. This works, and of course we are increasing the scalability. I mean, in this diagram, if we pay attention, there is more of these blocks being processed. There is 3 parallel sequence of blocks that can be processed. But what we have to remember is that those 1,000 validators were a lot more secure than these smaller subsets of 100 that we are creating. The concept of economic security is one that becomes even more important here. It's important to keep it in mind in that the security of these systems is completely proportional to the economic security that is backing the validators. If 1,000 validators together have $1 billion backing them, like the degree of economic security of a network, these smaller subsets of 100 would inevitably have less. So we are sharding our system entirely. We are sharding our execution, which is a good thing, but we are also sharding our economic security, which is not so much a good thing. And this is the original Cosmos model, by the way. I think nowadays with the interchain security, there is more thoughts on this, but in the very, very original Cosmos model back in, 2018, 2019, this was more or less their approach toward scalability. So beyond this fragmentation of security, because this is the first multi-chain approach that we're looking into, there's a few more properties to look at. So inevitably in this model, we have also introduced this undesirable pesky thing called a bridge, because we have split our one blockchain into now multiple blockchain. And this is inevitably a downside of a multi-chain environment where communication between these shards, these blockchains or L1s, whatever you want to call them, now has to go through something that is analogous to a bridge, and overall it's kind of slow. This is what I'm trying to demonstrate with my little turtle guy somewhere in there. That's one issue. And the other issue that I think is less understood and more underrated, but I think it's actually more important because one day it can lead to a black swan event, is that because we have now this multi-chain environment and they are communicating with one another and they have differing degrees of economic security, we have a problem that's called the weakest link problem, in that 3 blockchains are interacting with one another. They're sending tokens to one another and they're trusting one another. But one of them is significantly easier to attack. One of them is significantly cheaper to attack because it has less economic security because of this fragmentation. And this is a big, big problem that, well, again, it's like one of those problems that is not a problem until it's a black swan day, and a network goes down. To give you another example, like I am a blockchain backed by $1 billion of economic security. I want to then transact and send a message that implies I'm sending some tokens to another blockchain that is secured by $10 million. Like, isn't that a problem? This is what we refer to as the weakest link issue. So in multi-chain environments, especially those that don't have a homogeneous degree of security in these individual chains, this is a problem. All right, next model. This is where we get into the more Ethereum-style sharding or scaling. And we introduce this terminology of L1, L2 in this model. So optimistic rollups. In this model, we ignore any changes to the base validators. If you look at the top of the diagram, these validators and this system is more or less untouched in that it's not split or it's not sharded or anything. Instead, what we do is we conclude that, okay, let's not have all the work be done by this slow computer. Let's do the work somewhere else, somewhere off-chain, somewhere with less degree of security, and have this entity be called L2 or rollup or whatever you want to call it. And then we implement a system where we assume the work of this less secure L2 is secure, is honest or it's good. So the assumption is security unless proven otherwise by some other entities called fraud provers. So this is broadly speaking how optimistic rollups work. Work is done off-chain, assumption is that the work is done correctly. Fraud provers are constantly observing the system to detect any wrong behavior. A question that is, in my opinion, sometimes overlooked is that, okay, what if a fraud is detected? What should happen in that case? And in this case, I would assert that if a fraud is detected, then the L1, this secure computer, becomes actually like the jury. Now this L1 is like the judge of the system. If a dispute happens in one of these L2s, a fraud is detected, then the L1 have to step in. Then all the validators of L1 re-execute the thing, or should be able to execute whatever was disputed upon, and come to a conclusion. And broadly speaking, this is what is known as the fraud-proof system. And unfortunately, in many optimistic rollups, this is not fully implemented. As far as I know, it's pretty much on the roadmap of everyone, but it's worth noting that until these fraud proofs are in place, these systems don't really have a credible security to them. Another downside of the security of these systems is that they have a slower time to finality, because they don't have like a provable finality essence to them. Like it's kind of like the Bitcoin finality. It's like after a certain time has passed, we just we say it's good. We assume nothing has gone wrong. I think the norm these days is more like 1 week, 2 weeks, or something like that. So essentially, your time to finality is around like 1 to 2 weeks. And because this system is also introducing a concept of multi-chain, because we have like multiple L2s, again, it has the same fragmentation issue that the previous model also had. Now, what is good about this system, though, is that it scales very nicely, because in the absence of fraud, a new L2 is more or less no overhead on the L1, because the L1 is not doing anything for it. Like it's like the L1 validators are just sitting around doing their day-to-day stuff, like doing their own Ethereum L1 transactions. They're not dealing with the L2 transactions. There is a slightly more technical matter of data availability, as in these L2s do have to post their data to L1 at some point for further proving or for further evidence. And this data availability is an extra overhead with for example, if we add a fourth L2 in this diagram, there would be some extra overhead in terms of data availability, but it's worth noting that it's in terms of execution, there's very little overhead on the L1, and this makes the system overall scale pretty well. But yeah, fraud proofs are very necessary here. I want to emphasize that again. All right, next I have something new that I think no one has heard of. Has anyone heard of something called the cynical rollup? No, right? So maybe with my background you can guess where this is coming from, but I will get to it very soon. So cynical rollups are, as the name suggests, something vaguely analogous to optimistic rollups in that they offload the work to happen in less secure L2s, but they do the fraud proving somewhat differently. The fraud proving is happening proactively, and it's happening by other neighboring validators. So this means that, for example, when one of these L2s performs some work, it actually sends it to not all the L1 validators, but like a small subset of them. And this small subset does some initial checking. And then maybe some other small subset does a little bit further checking. But it never escalates in the absence of fraud to like everyone needing to recheck everything. So this makes the base security of all of these L2s a lot more secure, in that we can actually assert that the security of L2s with this proactive checking is actually as secure as the L1. This brings about two very nice properties in the cynical rollup model, being that one being that the finality time is now very fast, as in you don't have to wait like weeks. Because of this proactive checking, you can be wow. Crazy shit. I'll wait a little bit longer until everyone... Does it go off? Or?
I think you have to press on your cell phone to...
No, I did.
Okay.
I think there's still some people.
Yeah, you just have to like put volume down or something.
Very cool incident. Definitely makes this talk more memorable. Definitely makes cynical. Now you have a reason to remember cynical rollups. So again, cynical rollups, to recap a little bit, the main essence of it is that this fraud proving is proactive, and it's done by neighboring validators that are as secure as all the other L1 validators. And this brings about two very nice properties. That long time to finality goes away, and moreover, the security properties of these L2s becomes homogeneous, because we can actually assert that through this game of doing this proactive checking by the L1 validators, the security of all the L2s is actually equivalent to the security of the L1 itself. I am abstracting over a lot of things here. There's a recent paper by Web3 Foundation, the research institute that published and formalized this method. It's called ELVES. Again, you can't see it because it's on the third line, which is hidden. But you can find it in the slide, which is on my website. You can find it there. And it exactly formalizes how, with this game of having some validators check one of the L2's work and randomizing things in between them, we can hit these two properties that previously we thought were mutually exclusive, and that execution is mostly sharded between these L2s, but security is mostly shared between these L2s. So shared security, sharded execution. These are very two nice properties that cynical rollups bring together. There's a very nice analogy to demonstrate the difference between cynical rollups and optimistic rollups. So imagine you're all the validators of a L1, and in the optimistic rollup, I just come and stand here in silent. And if after 2 weeks none of you raise your hand, I leave and I assume everything's good. And that's how optimistic rollups more or less work. It's like you just like, without any proactive measures, I just wait until someone raises their hand. In the cynical rollup model, I enter this room, which is now all the validators, and I ask this person, do you have a problem? Like, do you detect a problem? And then this person gives me an answer. And then maybe I ask someone else, do you see a problem? And then I measure, and based on these answers, I can, with a few rounds of playing this game, I can be pretty sure that there was a problem or there was not. And indeed, if there was a chance of a problem in this situation, this very soon escalates to all of you. All right, that's a good TLDR on cynical rollups. And to be fair on it as well, the downside of it is that this proactiveness is not as cheap or as free as, for example, the optimistic rollup model, because in a fourth L2 added in this diagram is some extra work on the L1 validator. So the scalability is slightly less, but with in return for much better security guarantees. We can also kind of compare it like in that I think the execution is perhaps like a few orders of magnitude worth in the cynical rollup, but the time to finality is what, like 200x faster. So it seems like a good trade-off, or a trade-off that might be reasonable for many applications. All right, finally, let's get to the more a very fancy one, or the more mouthful one with the ZK snark and so on. These types of rollups are most often known as ZK rollups. I think that's a needlessly specialized words. Perhaps we should just call them snark-based rollups, or even more general, I would call them asymmetric rollups, because end of the day, they are all leveraging a property that is asymmetry of execution. So how do they work? They have the same property in that, okay, L1 validators are put as they are, nothing changes with them. The work happens on the L2 level, and these L2 guys are not economically secured, they don't have the money bags, but what they do instead is that these L2 validators do a lot more work, so they have to be really juiced up, and they generate a sort of proof that can be very cheaply verified on the L1 side to ensure that the work that they have done is correct. So we're leveraging asymmetric execution. L2 does a lot more work, and then L1 can verify it in a snap. And these succinct proofs are the most common ways to achieve this asymmetric execution. This system, as you see, has no need for fraud provers because these proofs are, they're mathematically correct. They are correct. They are as correct as 2 + 4 = 4 is correct. So there's no need for any fraud prover in this system. That's a very good upside of them. They are very secure. I really like this model for this property of it. The downside of it is that at the moment this asymmetry is kind of skewed. I think there was late last year, it was the numbers were somewhere around a million time more computation on the L2 side for the L1 to be able to verify it. And I think this year there was some big steps forward where it's now 50,000 times, but it's still a big gap. So depending on the demand, I think one way to put it is that these systems would be cost effective compared to, for example, the cynical rollup or optimistic rollup with fraud proofs if there is a lot of demand to justify this 50x or 50,000 times more computation that must happen on the L2 side to generate these proofs. But a very fast evolving area as well. And in 6 months, these numbers might differ, so we have to see. All right, so this is the little part where, because I have one more type of rollup that I want to introduce, and because it builds heavily on top of the Polkadot model, I need to just introduce you to two very small Polkadot terminologies. By now, and based on my affiliation, you might know that the Polkadot model works on the basis of the cynical rollup model. And in Polkadot, we call each of these subset of validators that can securely host one rollup with those properties of shared security, but sharded execution, and so on, a core. Because in Polkadot, we like this computer analogy. We assume Polkadot to be one big computer, and now Polkadot is like a multi-core computer. So each of these groups of validators are called a core, and each of those L2s are called a parachain, which stands for parallel blockchain. And Polkadot itself is already moving towards making the usage of these cores more flexible. So the Polkadot 2 code words upgrade is more about a few features that allow these cores to be used in a more flexible way. So for example, in the original model, these cores could be leased for some long period of time, 6 months to 2 years. Now it's flexible on both ends. You can use these cores one block at a time or a few blocks, or also you can scale up to multiple cores if you have usages. And also experimenting with lower block times. Again, I don't want to go into details of selling a pitch of a product here. It's more about the case that Polkadot already realized that these cores that work on the basis of cynical rollups have some unique properties, and we should make them more exposed to developers because they seem to have promise. And the last rollup model that I want to introduce, which is called Jam, takes this to the extreme. So let's have a look. So it's called Polkadot Jam because it's an upgrade that's coming out of the Polkadot ecosystem, and it's an upgrade to Polkadot, but in some ways it's like a very major revamp, so it has its own code word as well, which is called Jam. So what is Jam about? Jam is about gutting out all of these individual components of cynical rollups and exposing them to developers. So in the cynical rollup model, we can recognize that we have these three components that are available. We have some computation that happens inside a core. We have a data availability layer that's always available there. I mean, this is also available in Ethereum, it's available in Polkadot, it's available in all the L1s that host L2s in one way or another. And finally, we have some computation that happens on-chain. This is where the slow but very secure stuff can happen. And Jam is a protocol that exposes all of these primitives directly to the pieces of work that can happen to it. So this is one important property of it. And hopefully last time. And another and more important property of Jam is that it's extremely unopinionated about what type of work comes into each of these cores at any given point in time. So we no longer have these sequence of blocks that are tightly coupled to one of these cores called an L2 whatever. It's more like a big group of works that on every given time, some of them are grouped together and passed to one of these individual cores. So it makes very little opinion about which work items need to be grouped together and fed into a core at any given time, and this is completely left open. And I want to assert that doing this is really only possible with that shared security property that cynical rollups provide. And okay, you might still say, okay, what's the big deal about this? And I would elaborate on that next. I think this model introduced by Jam is a big deal, not because of Jam or Polkadot, because of how in the rollup landscape, in the scalability landscape, because it tackles a problem that we have seen in every single model, except for the hyper-optimized one, which is fragmentation. Persistent fragmentation. All of these models that we talked about suffer from persistent fragmentations, which means we scale the system by sharding it, and we call each of these shards an L2, parachain, whatever. And these shards are persistently walled from one another. If they want to talk, they have to go through this bridge, and then there was a whole arsenal of issues with bridge, and building bridges is hard. By the way, side note, building trustless bridges, really hard. And most bridges out there, not trustless, but that's a different topic. So Jam, through this flexibleness, the true flexibility that it has for its work items, and it gives them the ability to be fed into one core should they wish to communicate with another, and fed to different cores should they not wish to communicate to one another. And this basically means this need for having all of these bridges around to communicate data between these fragments goes away. So this is really I'm still learning how to articulate it. It's really a different paradigm and a step forward in the blockchain scalability, because it brings the best of both worlds into one another. In that it's scalable, but it has this element of allowing for synchronous communication when there is a need for it. You want to say about time? Okay, this is my last slide anyway, so we're almost done. Okay, this is basically just a summary. I'll be quick with a table. Let's see if everything is visible. Okay, almost. So, a very quick summary of everything we talked about. So, we want to scale this group of validators that are economically secured. The first model is the hyper-optimized model, where we don't really scale the system by sharding it, whatever. We just make that one system very fast. Is it economically secured? Yes, but I have this emoji to demonstrate that perhaps sometimes through these optimizations, we might be cutting corners. I can give you one example. So if the cost of running the hardwares of a network that operates on this model is so high that basically no individual other than a conglomerate company can run it, perhaps that's something that we should be skeptical of. But in principle, it's a system that is economically secured, as in it doesn't compromise that, and that's good. Is it homogeneous? This doesn't really apply here because there is no sharding. So the homogeneity is not a problem, and therefore, consequently, on the last column, it's not fragmented, and that is good. A sharded multi-chain, the Cosmos model, is it economically secured? But yes, but at the inevitable cost of less economic security for every individual shard, because we are sharding everything. As in, again, if you have 1,000 validators, we are splitting them into 500, and that's it, pretty much. So this economic security is not sharded, and it suffers from fragmentation. You can already see all the models, except for JAM, which you cannot see, which has a tick with an asterisk, which is, mostly suffer from fragmentation. Optimistic rollup with fraud proof, I want to emphasize the with fraud proof, they are economically secured. Depending on the implementation, they may or may not be homogeneous. So by this, I mean, if we look at, for example, the Ethereum landscape right now, we have a lot of L2s that are optimistic rollup. As far as I know, one of them has fraud proofs mostly implemented, all the other ones don't. So in practice, depending on which L1 is hosting these L2s, it might be homogeneous or not. At the moment, for example, in Ethereum, it's not homogeneous at all. But in principle, you could imagine an L1 which hosts many optimistic L2s, and all of these L2s have the same fraud-proof mechanism implemented, and then we can say this system is homogeneous in its economic security. And it's still not fragmented. Optimistic rollups without fraud proofs. Maybe here I'm being a little bit too opinionated. I think this is a non-starter, as in these systems really don't have any property of that original Bitcoin versus Revolut model in them. I don't see why these exist. Snark-based rollups, the asymmetric one, they are economically secured. In fact, they are very secure. They have pretty much the best security property of all of them. The same argument about homogeneity applies to them, in that if you have a lot of these snark-based rollups and they are all communicated with another, they are homogeneous. But if you have one of these secure snark-based rollup talking to an optimistic rollup that doesn't have fraud proof, then you have the same problem. So it very much depends on the ecosystem in which they are implemented. And finally, cynical rollups they are economically secured and they're homogeneous, but they are fragmented. And with this talk, I propose that perhaps JAM, this new predecessor to cynical rollups, is one that can hit all of these columns, in that the system is economically secured and it's homogeneously secured because it's cynical rollups. And it doesn't suffer as much from that persistent fragmentation because of other properties that I briefly mentioned. All right. So that's mostly it. Some closing thoughts or questions I just added at the last iteration of these slides.
I think we unfortunately don't have time for questions.
We don't have time, okay.
But thanks a lot for your amazing talk. That was a very great introduction to scalability. So I have a small present for you.
All right, thank you.
And yeah, next up will be a talk from Kian about modular blockchains. A big round of applause for the amazing talk.